Today we are going to learn about mastering UNet architecture for semantic segmentation. We will explore UNet structure, implementation, and optimization techniques to enhance your skills in semantic segmentation tasks.
Welcome to our video on mastering UNet architecture for semantic segmentation. In this video, we're diving into the UNet architecture, a revolutionary model renowned for its effectiveness in semantic segmentation tasks, particularly in medical imaging. Originating from the field of biomedical image processing, UNet has gained popularity due to its ability to precisely segment images. Today, we'll explore its structure, discuss why it's so effective, and provide a hands-on example of how to implement UNet in Python. By the end of this video, you'll have a comprehensive understanding of UNet, its advantages, and how to optimize its performance for your specific tasks. So, let's get started. UNet was introduced in 2015 by Olaf Ronneberger, Philip Fischer, and Thomas Brox, primarily designed to address the challenges in biomedical image segmentation. This architecture was a significant advancement as it was tailored to work effectively with limited training data, which is often the case in medical imaging. UNet was inspired by fully convolutional networks and was adapted to produce precise segmentations even with a small amount of annotated data. The architecture's ability to work with various types of images and datasets made it a versatile model, quickly extending its application beyond medical imaging to areas like satellite image segmentation and autonomous driving. The original UNet paper outlined its capability to learn from very few annotated images while delivering accurate segmentation maps, establishing it as a cornerstone in the field of semantic segmentation. The UNet architecture is distinguished by its symmetrical encoder-decoder structure. On one side, the encoder path, similar to a traditional convolutional neural network, CNN, consists of convolutional and pooling layers aimed at capturing the context of the input image by downsampling. Each downsampling step consists of two 3x3 convolutions, a ReLU, and a 2x2 max pooling operation for downsampling. The decoder path, on the other hand, is designed to reconstruct the image's spatial dimensions through upsampling and deconvolution layers. What sets UNet apart are the skip connections, which link corresponding layers in the encoder and decoder paths. These connections directly transfer feature maps from the encoder to the decoder, preserving spatial information that might otherwise be lost during downsampling. This architectural design allows UNet to generate high-resolution segmentation maps, making it highly effective for pixel-wise classification tasks.
UNet offers several advantages that make it a preferred choice for semantic segmentation tasks. Firstly, its design enables high accuracy in segmenting images by effectively preserving spatial information through its skip connections. This is particularly beneficial in applications where precise segmentation is critical, such as in medical imaging. Another significant advantage is its efficiency with small datasets, which is a common scenario in medical fields where labeled data is limited. UNet's architecture is versatile, allowing it to be applied across various domains, from medical imaging to remote sensing and beyond. Its ability to produce detailed segmentation maps makes it an invaluable tool for researchers and practitioners looking to improve the accuracy and efficiency of their segmentation tasks. Overall, UNet's combination of precision, efficiency, and adaptability is why it remains a popular choice in the field of semantic segmentation. Training UNet with real-world datasets involves several key considerations to ensure optimal performance. One of the primary challenges is handling diverse datasets that can vary significantly in terms of image size, quality, and labeling. Data augmentation techniques, such as rotation, scaling, and flipping, are often used to artificially expand the training dataset, improving the model's ability to generalize. Pre-processing steps, like normalization and resizing, are crucial for maintaining consistency across input images. Additionally, balancing classes in datasets is essential to prevent biases towards more frequent classes, which can be achieved through techniques like oversampling or using weighted loss functions. Evaluating the model's performance on a validation set is also critical to assess its ability to generalize to unseen data and guide further adjustments to training strategies. By carefully addressing these aspects, practitioners can effectively train UNet models on real-world datasets, enhancing their segmentation capabilities. Optimizing UNet performance requires careful attention to several factors. Hyperparameter tuning is crucial, as adjusting parameters like learning rate, batch size, and number of epochs can significantly impact model performance. Batch normalization can be incorporated to stabilize the learning process and improve convergence speed. Adjustments to the learning rate, such as using learning rate schedules or adaptive learning rate methods, can also enhance model training. Regularization techniques like dropout can prevent overfitting by adding noise to the training process. Additionally, fine-tuning pre-trained models on specific datasets can leverage existing knowledge, reducing training time and improving accuracy. By implementing these optimization strategies, practitioners can enhance UNet's performance, ensuring it meets the demands of their specific segmentation tasks.
Applying UNet in real-world scenarios presents several challenges. One common issue is class imbalance, where certain classes are underrepresented in the dataset. Techniques such as oversampling minority classes or using weighted loss functions can help address this imbalance. Noisy data is another challenge, particularly in medical imaging, where images may contain artifacts or low-quality regions. Pre-processing steps like denoising or using robust data augmentation can mitigate these issues. UNet models also demand significant computational resources due to their complexity, so leveraging GPU acceleration and optimizing code can alleviate some of these demands. Selecting the appropriate loss function is critical, as it influences the model's learning objectives. Finally, model convergence issues may arise, requiring careful monitoring of training progress and potentially adjusting learning rates or training strategies. By understanding and addressing these challenges, practitioners can effectively apply UNet to a wide range of segmentation tasks. Since its inception, several variations of UNet have been developed to address specific challenges and enhance its performance in various tasks. UNet++ introduces nested and dense skip connections, improving feature refinement and segmentation accuracy. ResUNet incorporates residual connections, enabling the construction of deeper networks while mitigating vanishing gradient issues. AttentionUNet integrates attention mechanisms, allowing the model to focus on the most relevant features within an image, enhancing segmentation performance. VNet is designed for volumetric segmentation, extending UNet's capabilities to 3D data, which is particularly useful in medical imaging for analyzing volumetric scans. These variations demonstrate UNet's adaptability, allowing it to be tailored for specific use cases and further expanding its applicability across different domains. By understanding these variations, practitioners can select the most suitable model for their particular segmentation task, optimizing performance and accuracy.
Let's dive into a hands-on example of implementing UNet in Python. First, set up your environment with necessary libraries such as TensorFlow or PyTorch, along with image processing tools like OpenCV. Begin by loading your dataset, ensuring you have both input images and corresponding segmentation masks. Pre-process the data by resizing images and normalizing pixel values to improve model performance. Next, build the UNet model by defining the encoder and decoder paths with appropriate convolutional and pooling layers, incorporating skip connections to retain spatial information. Train the model on your dataset, utilizing data augmentation techniques to improve generalization. Monitor training progress and adjust hyperparameters as needed. Once training is complete, evaluate the model's performance on a test set, using metrics like intersection over union, IOU, to assess accuracy. Finally, visualize the results by overlaying predicted segmentation masks onto the original images, providing a clear representation of the model's effectiveness. This hands-on example demonstrates UNet's practical application and offers insights into its implementation for semantic segmentation tasks. In conclusion, mastering UNet architecture for semantic segmentation offers significant advantages in various fields, particularly in medical imaging. We've explored the origins and detailed structure of UNet, highlighted its benefits, and discussed training and optimization techniques. Additionally, we've addressed common challenges and provided solutions, along with introducing UNet variations to suit specific tasks. Our hands-on example demonstrated practical implementation in Python, showcasing UNet's effectiveness in real-world applications. By understanding and applying the concepts covered in this video, you can enhance your skills in semantic segmentation and leverage UNet's capabilities for your projects. Thank you for joining us, and we hope you found this video informative and engaging.